Hi guys, and thank you very much for giving me the opportunity to present the tutorial. You are watching this because you have either downloaded our presentation on getting started with your design project. The example was based on the production of DEE from ethanol. However, in this case, in this particular example, I'm going to show you how to do the manual mass balance calculations, which will give you the inputs to your simulation manually. And to do that, I will not be using the DEE example. I'm just going to be using a generic example so that this particular video tutorial applies to everyone. It's not specific to DEE. I know students can get very confused when you introduce a particular product and they want to try and apply that information to everything that they're doing, even when they're not doing DEE, for example. So I'm going to do a generic example for this one so that at least this particular example covers a broader spectrum of students. So welcome and enjoy. This is the first of two tutorials for this particular presentation. The next video tutorial will be setting up Coco, or setting up your simulation environment. So let's get started. Now, the reactions that we'll be working with today, as I said, it's going to be generic. In other words, we won't be using a particular compound. So I'm just going to go with A plus B goes to plus 3B, right? And our second reaction will be A decomposing to 3F plus 2, right? So those are our reactions, and the other information that we've been given for this particular problem is that the product, which is C, right, is 50,000, right, tons per year, right? So that's the first thing we've been given, that our product is 50,000 tons per year. We know that we've also been given following. We've been given that our overall conversion is equals to 70%. We've also been given selectivity information, and it's as follows, right? So it says A goes to B by reaction 1 with a selectivity of 70%, right? Just gonna make space there. And then A goes to F by reaction 2 with a selectivity of 40. Let's go 60-40. I do not want to use the same amount as the conversion so that we avoid confusion. So if you observed my words while I was putting this together, I was saying that we've been given, we've been given, we've been given. But in most cases, for your design projects, the only thing they give you is how much product they want per year. They might give you the reactions, but you might have to go find that yourself. You're not given selectivity data. You're not given conversion data. You are certainly not given those, because those are things that you have to go look for. Now, at the beginning of our presentation, I gave importance to doing the literature review first. And this is where you get all this information, the conversions, your selectivity. That's where you get your reactor conditions. That's where you get your catalyst required and things like that, right? And then the other piece of information that we're given is that the plant operates for 330 days. days per year. That's our starting information. Now I'm going to erase this and then we're going to start with our calculations. All right. So the first things first that we're going to do is, oh yes, and then the last thing is because we're working with C, let's just specify that C has a molecular weight of 42 kgs per kg mole, right? Now, let's get started. So first things first, what we want to do is we want to we want to set some assumptions that will help us solve the problem. Now, in most cases, what they will do is they'll give you a purity of the product stream. Now, that means the product stream won't be 100% C, for example, in our example. Now, in the D example that we're working with here, the purity of the stream was 99.5. So as a first iteration, I will assume that the purity of the product stream is 100%. So first assumption is that purity of product stream is 100%. And then also, as a calculation basis, right, we will say we will use 50,000 tons per year of C in the product stream. Now, if you go back to your notes and your school notes, you'll know that selecting a calculation basis, what you want to do is you want to do that according to the stream that has the most information. And in our case now, the stream that has the most information is the product stream. Therefore, we're going to use it as the basis of our calculation. So there's that. All right. The next step is we are going to convert the 50,000 tons per year into kilomoles per second. So I'm going to draw my conversion table. I hope these will be enough. If you do not know this method, refer back to your textbooks. Otherwise, again, we do offer one-on-one tutorials. So I will definitely be happy to take you through what we're doing here. I'm just gonna reduce the font here so that we're able to fit in what we're doing. So we've got 50,000, right? Tons, and that's per year, right? We know that our year, according to the information that was given to us, is equals to 330 days, right? And we know according to our calendar that one day, or our clock, one day is equals to 24 hours, right? Because plants don't work like human beings. They don't switch off at 5, they run 24 hours. And we know that 1 hour is equals to 3,600 seconds. Now we're going to convert the tons. We know that 1 ton is equals to 1,000 kg, right? And we know that 42 kg per mole, right? So we're just going to divide by the molecular weight, which will be kg moles, right? 42 kg per 1 kg mole, right? And this will give us the total number of moles, which will be 0.04175 kilomoles per second. And that will be the n, let's call it N produced of C, right, will be equal to that. So that is the amount of C that will be produced by this process. I'm going to erase that and we're going to move on to the next section. Right? Next. So what's the next piece of information that we have? We know that the conversion to this process is what? Is 60%. So let's start working with the conversion so that we have as much information as possible before we look at the reactive mole balance. All right. So the equation for conversion. So I'm going to go through this step by step so as to try not to confuse anyone. So now I'm going to increase the conversion because we're probably going to work with the font. So percentage conversion, right, is equals to the number of moles that come in of A, right? I'm just going to write dot A, right, minus the number of moles that go out of A, right, divided by the number of moles that came in, right, that came in of A. And because we said percentage there, we would need to multiply that by 100. Now, if you don't want to multiply by 100, then you will write the equation as follows in the second line. And I'm just going to replace what I can replace immediately here. So that will be, now we're going to write the conversion as a fraction, which is 0.7 because we divided by 100, right? So 0.7 will be equals to, and then we know that the number of moles that came in minus the number of moles that came out of A, right? If you write that in reaction format, that will be the number of moles that came in of A minus the number of moles that go out of A, it will be N reacts A. And now this is important to denote that this is the total amount, right? And that will be divided by the number of moles that came in of A. Are we still together? All right, thank you. Next, we're going to look at the other information that we have. What do we have? We also have selectivity information, right? And our selectivity says that 60% of A goes to product C, and 60% of A that reacts, right, goes to product B. So now let's write this out, right? I'm going to erase that. So we've got that information. The next information that we have is that, let's see, the next piece of information that we have, I just want to start incorporating everything as we go so that it is understandable later. Okay, so let's write out the selectivity reaction. We know that N reacts A, right? And in brackets here, I'm going to put by reaction 1, right, is equals to only 70% or 60%, sorry, right, of N reacts A in total. Right? We're still together. So that's our first reaction, and we can almost immediately start replacing, because we know that per our last equation, we know that n reacts total is equals to this term here, n reacts total, which I'm going to multiply, I'm going to put here, right? So we're gonna substitute by 0.6, right, multiplied by the zero point 0.7 of, if you remember, n n n in dot a, right? It is 70% because that's how we wrote out the equation. If you remember, our conversion was 70%, right? Therefore, n reacts n react 1, the n reacts total is actually equals to n reacts total is 70% of n1 n in A, right? And x total is equals to 70% of n in A. So that is this term highlighted here. I hope we're still together, but basically what we're saying is that the amount of A that reacts is equals to the total amount of A that reacts, right? The amount of A that reacts in reaction 1 is the total amount of A that reacts in total multiplied by zero point 0.6, and that is represented by this term here, right? So every time when we want to represent n reacts A, right, we're going to multiply zero point 0.6 by zero point 0.7 by n1 in A. The next calculation we're going to look at is where we are going to calculate the amount of moles that came in of A. And the way we're going to do that is we're going to do that by doing a reactive material balance, where we're going to find the amount of, because we have a lot of information about reaction 1, because we know how much C is produced, right? And we know that in order to calculate the number of moles of A that react by reaction 1, so now I'm going to put that down here. So let me just put in my table, my equation. So the next point that we're going to use is that we know that n reacts A by reaction 1. This is very important to denote, right? And because from our equation, we know that I'm going to erase this part so that I'm able to put in everything the way I want it. So it's n reacts A and reacts A by reaction 1, and then the stoichiometric coefficient is 1, right? This will be equals to, and let's put in our divider there, our division line. This will be equals to n produced of C, right? And we know that it's only in reaction 1, so it can be noted, but already we know that. And then its stoichiometric coefficient is 2. It's 2, right? Therefore, n reacts, right? By equation 1, you will then say n produced C divided by 2, and what that will end up giving us, I think I had a value somewhere. Just give me a second. Let's see. Just give me a second. And reacts, that would be, that would give us a, we can then denote it as is equals to 0.5 n produced of C. So that's our next equation that we have. I'm going to erase that so we can go on to the next step. So with all this information, we are now able to calculate how much A came in, because what equation will that be, right? We had that equation, we had written it down. It comes down to what? It comes down to n reacts, right? N reacts of that equation that we erased just previously now. And if we put everything together now, what that equation will look like, it will be as follows. It will be the number of moles of A number of moles coming in of A, right, will be equals to, I'm gonna draw my, just want to make this very clear to everyone what we're doing, and then it's going to be, just go back to the, to be able to follow this better, you can just rewind and you'll see where all these terms come from. Uh, Number of moles produced of C, right? And then that will be divided by 0.42. Um, That's what the final equation comes to, 0.42. For those who are confused, that 0.42 is from that initial equation that said n react of A is equals to zero point 0.6 multiplied by zero point 0.7 multiplied by N1A. That's where the 0.42 comes from, right? And then this will then give you a total number of moles that came in of A as 0.049, right? And then that's how you calculate the total number of moles of A that came in. And then what you will then do is you will go on to calculate the rest. And then just remember that reaction 2 consumes 40% of what reacts of A, right? And then reaction 1 consumes 60% of what reacts of A. And then you will be able to compute how much D was produced, how much F was produced, how much C was produced in total. And then now what you will have is you will be in a position to draw your reactor, and you'll be in a position to say, um, just wanna do this, okay? You are now in a position to say A and B came out, right? And then it came in, and then what you will have at the end is A, B, C, F, and D. Now, according to my calculations, and this is something that I want you to do on your own, following the process that we followed, I've got a C of 0.04175. Let's just make some space here. I wanted to do that, yes. And then I've got a B. I'm gonna put a question mark. We'll discuss that when I'm done just giving you the other values. This is your homework to go and try and calculate this yourself. Um, Sorry, C A is actually not 0.0145, then C is not 0.04175, and then F is not 0.0139, then D was 0.071895. Now, why did I put a question mark on B? Well, B is the other reactant. It's the other guy. So I'm going to need you to come back with me, those who will be taking part in this tutorial. I'll need you to tell me under what conditions will you have A in your product stream. No, B in your product stream. Under what conditions will you be able to have C in your product stream? So I'm going to end this tutorial here, and those who've been following will see that I deliberately skipped some steps. So I basically formulated your equations using selectivity and conversion. I combined it to be able to give you how much A was in the process in the beginning. And then what you need to do is you need to go and figure out how to then compute the rest of the values that are given here. I hope this tutorial will be helpful. As I said, this is not throwing you to the wolves. This is me trying to help you get started, but also encouraging you to start doing things for yourself. And I hope this tutorial will be able to help you with that. I am available. My contact details will be at the end of this presentation, and I hope that we'll be hearing from you soon. And obviously, the A plus is if I don't hear from you, meaning that you were able to go ahead just by using this tutorial. Thank you and have a lovely day.